The major differences between the different states of matter really is how fast they're moving. Gas molecules are moving so fast that they can't be attracted to each other. In a liquid, they're moving more slowly so they can get attracted to each other, but they're not so attractive that they permanently stick. And then in solids, you have them moving so slowly that the attractive force is enough to hold them tight together, and so they jiggle in place. The attractive forces that cause molecules to stick together are called, we call them intermolecular attractive forces, and there are three of them. London dispersion forces, they're also called induced dipole forces and van der Waals forces, dipole-dipole forces, and then hydrogen bonding. By understanding intermolecular attractive forces, we can then understand the physical behavior of molecules. London dispersion forces are due to electrons in one molecule being attracted to the protons in another. And what happens is the electrons are moving around, and at any one time, they are not going to be always evenly distributed around an atom. So there will be a slight negative on one side and a positive on another, and those dipoles then, it's called a temporary dipole, then are attracted to each other. So anything that has electrons and protons has this London dispersion force, because all covalent compounds have protons and electrons. All of them are going to have London dispersion forces. And because the bigger a molecule, the greater mass it has, the more electrons and protons that it has, well then the larger the molecule, the bigger the attractive force between the molecules due to the London dispersion forces. This is a picture of it. Two heliums can have a really tiny attractive force. And I'm showing the electrons on one side of the helium. So if they're next to each other and they're moving slowly enough that they can actually exert this force on each other, the electrons in one atom are actually being attracted to the protons in the other. We call this a temporary dipole. We will also call it an induced dipole, because if one helium atom has a little dipole in it, it will cause the electrons to move in such a way that the other one will have one too. But the book calls it London dispersion forces, and for the most part, I'm going to call it from now on London dispersion forces. Now, if the atoms are moving slowly enough, the attractive force can work, and they start sticking to each other. So we see a relationship between the speed of movement and how much they stick to each other. Cold atoms move more slowly, so the colder things get, the greater the attractive force can work, and so a gas, if gets slow enough, will start liquefy, or it can even solidify if it's moving that slowly. And pretty much all matter can be brought to a liquid or solid state. So what do you need to remember about London dispersion forces? All molecules have it. As mass increases, velocity decreases, and as mass increases, the number of positives and negatives increase. So what we see is with an increased mass, you have an increased London dispersion force. The second intermolecular attractive force is the dipole-dipole attraction. We see this in molecules that have permanent dipoles. Look at these molecules here. This molecule right here has a permanent dipole. What is a permanent dipole? Permanent dipole are in polar molecules. So any molecule that's polar will have that permanent dipole. The oxygen has a del negative on it, and this side of the molecule with the less electronegative carbon and hydrogen has del positive. And what happens is the negative on one molecule will be attracted to the positive on the other. So any molecule with a permanent dipole will have this dipole-dipole attraction. The atoms on the outside of a molecule are one way of recognizing a molecule that is polar. Or if the central atom has non-bonding pairs, and a non-bonding pair or two non-bonding pairs or even three. So if I were to draw the Lewis dot structure of this molecule right here, you would find that oxygen has two non-bonding pairs on it, and that's how we can identify that it is a polar molecule. The third intermolecular attractive force is hydrogen bonding. We see this in molecules that either have an oxygen-hydrogen bond or a nitrogen-hydrogen bond. Before I go any further, I want to explain something that is confusing to students. When they hear hydrogen bond, they think of a bond, and you might look at this and say, well, that's a hydrogen bonded to an oxygen, so that's a hydrogen bond. That is not a hydrogen bond. This is a inappropriate name for what we're talking about. Hydrogen bonding is an intermolecular attractive force. That means between two molecules. So it is not a bond, but an attractive force. It's just gotten the name hydrogen bonding from the get-go, and students get very confused. Now, if I look down at these two water molecules, I'm showing a hydrogen bond between them. This is a covalent bond, this is a covalent bond. This is a covalent bond, and this is a covalent bond. And there is an attractive force between the del negative on the oxygen and the del positive on the hydrogen. What do? We draw a dotted line, not a line, but a dotted line for the attractive force between the oxygen and hydrogen. And this dotted line here has the name of hydrogen bond. Now, we see it in molecules that have oxygen-hydrogen covalent bonds or nitrogen-hydrogen covalent bonds. Water has this hydrogen-oxygen covalent bond, so it can form this hydrogen bond. Why is it that this happens? The reason is that you have a hugely electric oxygen atom and a hydrogen that is very small electronegative, and they're tiny atoms. And because they're tiny and they have a very large dipole due to the great difference in electronegativity, it makes an extremely large dipole-dipole force that we call hydrogen bonding. So it's really basically a type of dipole-dipole force. Again, nitrogen-hydrogen bonds allow hydrogen bonding. Why? Because a large del negative, large del positive, and a large del negative can be attracted to a dipole in another molecule. The hydrogen bonding actually occurs on the non-bonding pairs. So we draw the hydrogen bond between a non-bonding pair and a hydrogen attached to an oxygen on another atom, or here from the non-bonding pair to the hydrogen attached to a nitrogen. This is the strongest of the intermolecular attractive forces. In fact, if we look at the order of attractive force, we consider London dispersion forces to be the weakest, dipole-dipole forces to be intermediate, and then hydrogen bonding to be very strong. So it's a strong intermolecular attractive force. However, it is much weaker than a covalent bond. Students will often hear that hydrogen bonding is very strong, and then they'll hear hydrogen bonding is very weak. Well, hydrogen bonding is very weak compared to a covalent bond, but it's strong compared to the other intermolecular attractive forces. Here is an example of water hydrogen bonding to itself. I have 5 water molecules, hydrogen, oxygen, hydrogen, and I've drawn in a vector dipole to show you positive on the hydrogen, and negative on the oxygen. We'll bring these close to each other, and when we do, we see that as they move to each other, they orient themselves so that negative is next to positive, and then we draw dotted lines for the hydrogen bonds. Always remember that it's a del negative on the oxygen or nitrogen and del positive on the hydrogen that cause the hydrogen bond. So to summarize this, London dispersion forces are weak for small molecules. However, if you get a very large molecule, it increases with molar mass, so you can get a large London dispersion force with a large molecule. Dipole-dipole forces are moderate forces, and they're found in molecules with permanent dipoles. Organic molecules that have oxygen and nitrogen have permanent dipoles. Hydrogen bonding is the strongest of the intermolecular attractive forces, and we find it in molecules that have an OH bond or an NH bond, like water, methanol, ammonia. And you'll when you see the oxygen or nitrogen, you know it has a dipole force. Then you look to see, does it have a hydrogen attached to the oxygen or nitrogen? If so, then hydrogen bonding exists.